Hey, welcome back. Today we're going to be just finishing our notes on probability. We're going to be starting here with the law of large numbers. The more trials that are conducted, the closer the results become to the theoretical probability. Now, remember yesterday we talked about theoretical was basically like a coin. You could flip it, and it doesn't matter. You're going to have 50, theoretical is you have one out of two chances. One time it's going to be a head. Out of two, it could be a heads or a tail. So your probability is 1/2. Um, there's two chances, two options, and you only want one, so it's 1/2. The experimental probability is you might flip a coin 10 times, and 7 of those times it turned up heads. So the experimental probability we said be 7/10 or 70%. What we're saying here is the more times you do a trial or an experiment, and that's what we're saying right here, the closer you're going to get to the theoretical probability. 10 times for flipping a coin is really not a whole lot. Flipping it 100, you're going to get an answer that's a lot closer to the 50%. Trial 1, toss a coin 5 times. Well, there's the example, and it was 3 out of 5, so they got 60%. 3 out of 5 is 0.6, which is 60%. Trial 2, they did it 500 times, and you found out that the percentage was 50.2%. But the difference here then obviously is the fact that in the first trial they did it 5 times, in the second time they did it 500 times. So our theoretical probability is 0.5, but in each of these cases the experimental probability was not exactly 0.5. All right, let's talk about and with probability. All right, and is an important thing that we need to discuss. Um, if we have independent events occurring simultaneously, the product of individual properties or probabilities. It's the product. Product meaning the multiplication of the individual probabilities. If events A and B are independent, then the probability of A and B occurring is, and notice that what they're showing here is the probability of A and B. Well, take the probability of the first event and multiply it by the probability of the second event. So, for example, let's say the probability of rolling a dice and getting a 5, and then you're going to flip a coin and get a heads. Well, the probability of 5 is 1 out of 6. The probability of a head is 1/2. So the probability of both of those events happening at the exact same time is 1/12. All right. Here they're doing the exact same thing, except they're talking about two different, or rolling a die. One die is going to roll 4 times. So we want. I'm sorry. One die is going to be rolled once, and we want to get a 4. So how many desired outcomes? 1. We want to get a 4. How many possible outcomes? Well, there's 6 sides to a die, so it's 1 out of 6. The second die that's rolled, we want to get a 1. How many ones are there on a die? There's 1 of them. There's 6 sides, so it's 1/6. So what is the probability of rolling a 4 and then a 1? Well, it'd be 1/6 times 1/6, which is 1/36, or 2.78%. Okay, or. Whenever you see the word or, it means addition. Independent events occurring individually. It's the sum of the individual probabilities. If events A and B are mutually exclusive, then the probability of A or B occurring is, we're going to take the probability of A and add to it the probability of B. So an example of this would be rolling a 3 and flipping a coin and getting it tails. Well, that is 1/6. A 3 happens one time out of the 6 sides. A tails is 1/2. So we're going to add these two. An or statement, once again, we're saying rolling a 3 or flipping a tails. Either one of these two things can happen. So that's going to be 1/6 plus 1/2. Well, we got to find like terms or common denominators. And 1/2 becomes 3/6. So we get an answer of 4/6, which equals 2/3, which equals approximately, let's say approximately, 67% chance of you rolling a 3 or flipping a coin and getting a tails. Here they go through the same thing. of rolling a 4 and rolling a 1. You could roll a 4 one time because there's one 4 on a six-sided die, so it's 1/6 again. Rolling a 1 is there's one 1 on it. There's six possible outcomes, so it's 1/6. If you add them, you get 2/6, which is 33%. Okay, probability still. Now we're going to talk about not. Independent event not occurring. It's 1 minus the probability. So this not really means we're going to take 1 minus whatever the probability is. So what is the probability of not rolling a 1 on a die? That means there's 5 options. So this is a really good chance this could happen. All right. So the way we end up finding probability of this is it's 1 minus the probability of that event actually happening. Well, rolling a die is going to happen one time out of 6. Rolling a 1 on a die is going to happen one time out of 6. So it's 1 minus 1/6, which is 5/6, or 83% of the time, you're going to roll a die and it's not going to be a 1. All right, let's break this problem down. Two cards are dealt from a shuffle deck. What is the probability that the first card is an ace and the second card is a face card or a 10? So this is some really complicated probability, really. We're going to break it down. First of all, how many cards are in a deck? That means there's 52 cards. There's 52 possible outcomes. How many aces are there? There's 4. How many face cards are there? There's 12. How many 10s are in a deck? There's 4. So I'm seeing an and statement and an or. So up here for this and statement, we're going to end up multiplying for the and statement, and we're going to have to do some addition down here for this or statement. All right, so let's break this down. First of all, what is the probability that the first card is an ace? Well, there's 4 aces, so there's 4 chances that you could pull out an ace. There's 52 total cards. So it's 4 out of 52 that you could have is the probability that you could pull out an ace on the first one. It'd be 1/13 or approximately 7.7%. Since the first card was not a face card, what is the probability that the second card is a face card? Well, we're going to say there's 12 face cards. But now there's only 51 cards left because we've already pulled one out. So there's one less. It's not 52 anymore. It's 51. So it's 12/51, so 4/17, which is 23.53%. The other option then is if the first card was not a 10 because it was a face card or a 10. So now there's only 4 10s. So there's 4. There's still only 51 cards. So what we're dealing here with, this part right here, is the second part of our statement. And there is a 7.84% chance that the second card was a 10. So what we're working on here is we're still working on this problem. We have this and statement. And this and statement again is multiplication. So the probability of pulling out an ace, and that's what they're saying here, probability of an ace. And means multiplication, so they have an and multiplication statement there. And then we have the second part is the face card or a 10. Well, what does or mean? Or means addition. So really what we've came up with here is that now that we've found these probabilities, we can plug them into our equation. Remember that the probability of an ace was 7.69%. The probability of it not being an ace but a face card, the second one was 23.53, and the probability of it being a 10 on the second one is 7.84%. So let's plug these into our equation. I'm going to say approximately 7.7. This right here, the probability of the face card was about 23.5. Probability of a 10 was about 7.8. I'm off there a little bit, but I'm not going to flip back again. And now we're just simply doing what it tells us. I paused it here and had to do it. We can't multiply the percentages, but we can multiply the decimals. All right, when we do this part right here, we have to do it as decimals. And that's going to give us then the 0.235 plus 0.078 gives us 0.313. If we multiply that by the 0.077, we end up with a 2.41% chance that we pull out an ace and then either pull out a face card or a 10. if the first card is an ace, what is the probability the second card is a face card or a 10? Well, um, what that does here then is this is a different problem, and let's figure out how they got that. All right, the second one here. This first thing, if the first card is an ace, we don't have to find the probability of an ace. That's not the question. What all that's telling us now is instead of there being 52 cards, there's 51 cards. So what I've done here is this is an OR statement. It's an OR statement, which means we're going to add. So what's the probability of a face card? And it's not 4 out of 51. I just caught a mistake I made. There's 12 face cards in there. There are 4 10s in there, so it's 12 51s plus 4 51s, which gives us 31.37% of the time you're going to pull out a face card or a 10 on that second draw. Hey, this is great for today. I'll see you on the flip side.